Can you hear me? Dan, can you hear me in the back? Apparently not. Yes. Can you hear me in the other room?
Okay, you don't want to stand right in front of that speaker.
Sure. Is that good? A little bit of feedback. Thank you.
Is the speaker here? Is this
Yes.
one working? Right? Okay. But we're still getting sound from the other session?
A couple of minutes ago, yes, but let's try it out. So,
Okay, ready.
all right.
The speakers and share this one.
Okay. All right, so I think we can get started. Thanks for coming out this early, and welcome to our tutorial on data management in machine learning. Let us maybe start with a little bit of an introduction of ourselves. So this tutorial is joint work with Arun Kumar, who worked essentially on UDF-based systems for declarative feature engineering and factorized learning. I'm Matthias Böhm. I work on the optimizer and runtime of SystemML, which, by the way, just yesterday graduated to a top-level Apache project. And we have Jun Yang, who worked on statistical analysis in the Riot project in Cumulon, which aims for deployment in the cloud. Now, let's have a look at the motivation. So essentially, we want to make a case for data-intensive machine learning. And there are many facets to that. The first facet is an application perspective. So we see today more and more really applications that try to build data products. And there we can see the entire application essentially as one large data pipeline. There's also a workload perspective. So it is important to realize that machine learning workflows are very repetitive, including that we have iterative training algorithms, and those training algorithms often rely on I/O-bound operations such as matrix vector multiplier. So on the right-hand side, we see, for example, a typical roofline analysis that is a good visual tool to just understand what is the bottleneck in our application, where we plot essentially peak compute bandwidth, and depending on the
Hi, good morning, everyone. So welcome to this tutorial. I know this is the last day of the conference, and we also separated into many tutorials and workshops. So, but this one is a very interesting one. So I will first give you a very brief introduction on what this tutorial is about, and also the speakers, and then we can start. Okay. This tutorial actually is a very useful one because we know we are facing with very big, massive amount of data. But the majority of the data actually is unstructured. It's massive text corpora. How to turn this massive text corpora into structured data, put it into a structured database, will be a very important task for database researchers because it's a big enabling technology. You will enable the real-world massive amount of data, and then the very advanced database technology can be applied. Okay, so this is why we have been working on this direction. I'm going to introduce all the four speakers, then I'll pass to the first one. Okay, the first speaker, Xiang Ren, who is a graduating PhD. He will be graduating in the summer in UIUC, Computer Science Data Mining Group. And he already accepted the faculty position in University of Southern California. before he joined USC,
They are
likely he
currently
would
trying
do a
to
very
fix that.
short, half a year postdoc, maybe in Stanford or someplace. He got a PhD 2016 Google PhD fellowship on structured data and database management. In 2016, Google internationally only give one PhD fellowship in this category, structured data and database management. He got it. Okay, so that's why he's one of the
Yes,
leading
right.
PhD student researcher working in the sphere.
Until also
Then the second one is Dr. Meng Jiang. Meng is here. Okay, he got a PhD in 2015, I should say, in Tsinghua University in China, which is ranked #1, both in engineering and also in computer science. And he got a PhD dissertation award in computer science, Tsinghua University. You probably can see this is almost like ranking #1 in Tsinghua in computer science. During his PhD, he worked with Christos Faloutos at CMU for 10 months or so, generated many research papers. Some paper even got like a KDD,
those are
like a mass paper award
So first we're going to look at
and
how we can
he
integrate
worked
machine learning
at
into data systems.
UIC as postdoc
And second, the other way
for
around,
close to 2 years.
How
And
can
he
we
will
build
join
machine learning
in
systems
August.
and
He will
leveraging
join
essentially
Notre
database
Dame
technology to
as
speed up
assistant
those training
professor.
algorithms.
Will become
And
faculty
finally,
in
we
Notre
want to
Dame.
also
Okay.
broaden the
So
scope,
that's
not
Dr.
just
Meng
look at
Jiang.
training, but really
Jingbo
look at
Shang
systems
is
that
a
try to
PhD
simplify and
student,
cover the
currently
entire
in
end-to-end
computer
life
science
cycle,
in
for machine learning
UIUC.
applications.
Interestingly,
now, this is the current landscape.
2017 Google PhD fellowship in the category of structured data and database management give one award in North America. They give it to him.
And our goal for this
so
is essentially
of course there's another one in Europe. Okay, so total in the world maybe there are only 2 in this category, and he's currently doing the competition on the programming in San Francisco. He could not join us, so I will speak for his part. Okay. Then the last one is me. Okay, so you probably saw me in both database and data mining conference quite a lot. I probably do not need any self-introduction. I'm just a professor, a Bear Bliss professor, a chair professor in computer science at UIC. So we are very close. We just drive down here. Okay. So let's start with the general introduction and the context.
Techniques to whenever you're building your own machine learning system. And finally, we also provide an overview of just existing open research challenges and how we can potentially address them. Now, it is important to realize what this tutorial does not cover, because machine learning is a huge area. So first, we will not aim for a general introduction into machine learning, nor into general purpose systems such as graph-based systems or data flow systems. We will also not cover deep learning because this is a sub-area that has very specific workload characteristics and very specialized systems to deal with those. Other survey papers already covered that, and it just deserves a very own tutorial because in comparison to traditional machine learning algorithms, those algorithms are usually not data intensive, but rather compute bound and require special accelerators. Finally, we will also not cover RDBMS internals. So there is recent work on, for example, learning cost models or trying to do workload prediction, essentially leveraging machine learning for DBMS internals. So this brings us to our tutorial outline. So as we already said, we want to cover those 3 major areas of systems. We're going to start with just query generators and how people integrated machine learning via UDFs into existing systems. Second, we will focus on factorized learning and also partially deep integration into RDBMS. In the second major category, we then talk about really simplification rewrites, operator selection, and operator fusion, as well as at runtime level about compression, scan sharing, and index structures. If there's time, so at any point, please interrupt us. We want to make this a very lively tutorial. So if due to many questions, we run out of time. We're going to drop the part on cloud elasticity. So how do we deal with preemption and failures in such a cloud scenario, and how do we provision for those kinds of scenarios? And finally, we broaden our view and look at feature engineering, model selection, and model management. And finally, a little bit of an overview of existing problems and final Q&A. This kind of sets the stage for our first topic on query generators and UDF. And with that, I would hand over to June, unless there are any questions so far. All right.
All right. Thank you, Matthias. Sorry about the audio problem. And in fact, what I'm going to do is I'm going to fix some things up first for the live stream, so make sure that our sound is being recorded. So bear with me. Apologize for the delay. Let's hope this works. All right. Okay. Again, my sincere apologies. I'll speak as loud as I can. So, what I'm going to talk about to start off is how do you do machine learning with just SQL, and perhaps with the help of UDFs. And the main takeaway point is really this. Okay, if you got something like a hammer, then everything looks like a nail to you. And actually, in this case, the hammer is actually very powerful. So over the years, these commercial database system vendors and even open source database systems like PostgreSQL, they've added a lot of functionalities, and they have remarkable extensibility over the years, right? You give us XML, we'll add it. You give us market basket analysis, we'll add it. You give us machine learning, we'll add it. You know, everything's in there. And it's actually quite nice, right, to have a single platform where you can do all of this, you know, all steps of this analytics pipeline, all in one framework. That's a lot of convenience. And it's also efficient, or has the opportunity to be very efficient, because you're moving the analysis closer to the data, right? You're not copying all this data out just for doing some number crunching outside of the database, which is a lot of overhead. So also, by having all these different steps in one single system, allows for the opportunity to co-optimize various steps together. So that opens up more room for improving the efficiency. And last but not least, we have declarativeness. And this is something that our community has a lot to contribute. So basically, by declarativeness, I mean you write what you want, not exactly how you go about implementing it. Right? So this allows for automatic optimization, which further helps scalability and efficiency, as well as resource elasticity. Right? So this is one area where our community has plenty to offer, because we have all these years of experience developing this very nice declarative interface for database systems. All right, so here's my roadmap for this very brief section of the tutorial. I'm just going to start very simple, slow and easy. We're going to walk through some examples where you can take some machine learning, and then we'll just put it into SQL. I'll start with the basics, matrix multiply, nothing fancy, and then move on a little bit to ordinary least squares, and then we'll move up again the food chain, gradient descent. We also have examples for things like k-means and also MCMC. We don't have time to cover all these details, but we will post the slides afterwards, so you can check out the details if you want to. And then after seeing all these examples, I'm going to give you just a brief discussion on the approaches of using SQL to do ML. So let's start with the simples. Matrix multiply, okay? So consider two matrices, A and B. Okay, you can represent them simply as two tables. Right? So I is the row number, J is the column number, and value is basically the value at this particular entry location within the matrix. Right? So this is basically a sparse representation of the matrices. And you can actually just write matrix multiply using this join followed by group by and then finally aggregation. Right? It's easy to see, right? If you want the element in the result matrix at ij, this basically amounts to looking at all the elements in matrix A with row number I, and all the elements in matrix B with column J. And you basically pair them up and multiply them and then you just sum up the total, and that gives you the exact value for that output element. So this actually works pretty well for sparse matrices because with this representation, you don't really have to store any zero values in here. Okay, so you only have to store the non-zero values. So that's good. But this is not that good for dense matrices, right? Because the
This is good.
this is good now.
Yeah, you can
Okay,
use that.
great. So
The handheld. Do you know where the handheld went?
all right.
The mic? Handheld?
So we're good for now. Okay.
Okay, that'll
All right.
work.
Okay. So this is not so good for dense matrices because this is a lot of overhead, right? For each entry, you're storing the row number, column number. For each float or double, you're storing 2 more integers. It's not that efficient, but still, this beats quote unquote the small data platforms that you typically use for linear algebra. So for example, if you have just a R program loaded on your laptop, you try to read a gigantic matrix, okay, it doesn't quite fit into your working memory, then you start to thrash. And in that case, database system already give you I/O efficiency, knows when to bring in data, when to flash out data, and all that. So you get this automatically for free. So even in those cases, even though this has a lot of overhead and so on, it's pretty efficient. Okay. Now, if you want to be a little more efficient, you can say, okay, instead of storing these individual values one by one, let's store rows and columns. Okay, so in this representation, matrix A is stored as a table, basically in row major order. Right? So for each row, you store this vector of values for that particular row. And for B, you store in column major order. And now you can do matrix multiply using just a simple, very simple query, which basically do a cross product between A and B. And then you do the dot product of the row vector and column vector, and that's it. So this dot product here will rely on a user-defined function that takes 2 vectors and numbers and produce the dot product. Pretty straightforward. And this works fine for dense matrices. The encoding is pretty efficient. But it's not the most optimal. Okay, I want to give you just a very simple geometric intuition here. So imagine you're doing a matrix multiply of this x and y over there. So it's m by l and l by n. So the result matrix is basically m by n, right? Okay, so how much data do you have to read or write for this operation? Well, you have to read the entirety of x, y, and write out z, right? So the total amount of data you write is kind of like the area, right, for these 3 rectangles. Right? So now imagine you fold up these 3 rectangles and you turn that into a cuboid. Okay, so that's kind of like the amount of I/O you have to do is basically the surface area of this cuboid. If you count the number of multiplies that you're actually doing, it's actually the volume of this cuboid, right? It's m times l times n. Okay. So now we can imagine if you have very skinny matrices, like this is a row, this is a column, it's not a good deal, right? Because you have a lot of surface and not much area. So for the same amount of I/O, you're not doing that much computation. Where you say, for example, you're reading order n data in, but you're only doing order n multiplications. However, if you switch the aspect ratio of these guys to like blocks, like squares, then for n square stuff you're reading, you actually can do n cubed multiplies. So it's a much better deal. So multiplying just rows and columns is conceptually simple, but not always the most optimal thing to do. And also note there is a slight change in the representation from the input to the output as well, right? You start out with a row and column major representation, you end up with basically a sparse representation. If you want to convert them, you can still do an aggregation query on top of this. That's all right. No biggie. If you really want to explore the full possibilities of playing with the aspect ratio of these units and multiply, then you can use this block layout. So here you still have this ij. So these are the row number and column numbers for submatrix, or sometimes they're called blocks or tiles, if you will. So these are essential submatrices you're storing in this third attribute B. Okay? And then to write the matrix multiply, it's almost the same as the first representation, but instead multiplying numbers together, you're multiplying matrices together, submatrices together, and summing up the result of these multiplications. So for those two, matrix multiply, you need a user-defined function, and for summing up a set of matrices, you need basically a user-defined aggregate, which database systems also support. So again, you see this very easily encoded in SQL with a little bit of help of UDFs and UDAs. And here you get to choose what your desired V is. You can choose the right aspect ratio. You want to make it big enough so that when you do the UDF, You can actually just call it an optimized library. You load up 2 big matrices and do blasts on it, and then you get a result back. Okay, so now with those simple linear algebra matrix operations, you can do already a lot. So for example, if you want to basically fit a linear model, you can do ordinary least squares very easily in SQL. Right, so here what we're trying to do is we basically have a set of observations. Their values of the features are captured in X, and then basically these variables, these outcomes that you want to explain are captured in the column vector Y, right? And you're looking for basically the parameter set in beta that best explain these observations. So the best fit actually can be expressed in closed form in this formula. So it's X transpose times X, matrix multiply, and then take the inverse of that, and then matrix multiply with X transposed, and do a matrix column vector multiply with Y. Okay? Every single step is basically something we can express in SQL. Well, maybe I lied a little bit. Inverse is always problematic. So a lot of these systems basically say, oh yeah, if you have an inverse, what we do is we define a UDF that takes 2 matrices, and we'll just do it in memory using some optimized library. We'll spit out output. Okay. You know, so it's kind of like cheating, but it's not a big deal, right? In this case, if you look at the dimensions of that inverse, right? So X transpose times X is basically the number of features times the number of features. So that's tolerable. It's not like a number of data items times the number of data items. Okay. All right. So what's the point so far? We've seen that just using SQL and UDF and UDAs, you can do a lot. And in fact, it's not limited just to matrix multiplications and these simple things. You can actually do quite a lot more, and we'll see some examples. The fact that most of the UDFs nowadays in these commercial systems, they actually allow you to do a lot of things. You can just plug in arbitrary hard code, not arbitrary, but R code, Python code, anything you want. You can do it, you can make these UDFs at the tuple level, so these functions can be invoked in the select clause and where clause. But you can also write UDFs that are essentially like application programs that call SQL statements and do things. So this gives you great flexibility. Although if you put too much stuff into there, then the database optimizer doesn't get to work. So there is a trade-off there. But I want to highlight this one special class of user-defined functions. These are UDAs. And given that this is a database conference, I don't think I need too much explanation here, right? So user-defined aggregates, you start with basically an init function that initializes the state, and you have accumulate function that basically takes additional data, then you update the state accordingly. And then you have optional merge function that basically can take partial results, compute it over different subsets, and combine them to get a result for the combined set. And then you have a finalize that produces the final answer from the state. This pattern, interestingly, covers a lot of the computational patterns that arise in machine learning, because this basically captures the essence of iterative computation. Okay, and in the backup slides we have, which we'll post online, you can do k-means using just UDA, right? And next, I'm actually going to describe how you do a gradient descent in UDA. So, but just a little bit of background for those of you who just need a quick intro. So gradient descent is basically an optimization procedure, right? So you've got this data D, and you're trying to basically figure out some parameter that best explains the data, W. What you're trying to do is solve the following optimization problem. I want to minimize some kind of loss function defined over W and D. Okay? Now, in a lot of cases, solving directly for the optimal of W is hard, but you can take an iterative process. You start with some guess, okay? And then in the next step, what you do, you update this guess in the direction of the gradient of the loss function at the current guess. Okay, you just rinse and repeat until it converges. So intuitively, you can think of just somebody or your drop of water following the stream, trying to look for the bottom of the valley, right? You follow the deepest descent path down, and then you get there. So if the function is convex, then you will get basically the global min. And when you do this gradient update step, a lot of times you can basically compute this gradient over the entire data set. In some situations, the loss function is actually linearly separable over the data set. So you can basically break it down into the summation over something that's to be computed on individual data items. So in every step, you're basically computing this sort of aggregation over the entire data set to do the update. But in fact, there's something else you could do. Instead of computing this full gradient on the entire data set, what you can do in each step, you just take one of those data points in your data set and update your gradient accordingly just from basically this individual chosen single point. So that you can do in a step as well. So that's called stochastic gradient descent. And actually works pretty well as well under certain conditions. So you'll also get converged to the global minimum, right? Even if you just pick an arbitrary order of points to process in the data set. So how do you do this in SQL? If you want full gradient descent, full gradient update in every single step, then what you can do is you can code that step using a user-defined aggregation function, right? Because if the function is linear separable, then obviously you can write it over some kind of user-defined aggregation function using those init, accumulate, and so on and so forth. So every step will be a SQL query. And the outer loop can be driven by another kind of driver program that's coded in UDF or of some sort. But if you want to do stochastic gradient descent, every time you only have to consume one data item. So in fact, the entire iterative procedure can be coded as one single UDA invocation, where the accumulate basically takes care of one step of update. So it's a really neat approach where you can basically encapsulate the entire procedure into one single UDA. I'm just going to very briefly mention MCMC. So UDAs can do database and SQL and UDA can do a lot more. So MCMC is basically a sampling-based approach towards inference. And it's used a lot in Bayesian machine learning. So what you do here is you have basically a joint distribution that you want to do inference on. It's too hard to work with the form of the distribution directly. So what you do, you just repeatedly draw samples, Monte Carlo approach, right, from this distribution. And then you're going to look at a clustering of samples and get the quantities of interest that you want. Okay, so interestingly, it involves basically generating samples and analyzing collections of samples. So for generating samples, hey, we're just going to define a user-defined value generating function. Okay, for analyzing basically all these samples together, we'll just treat the collection of samples as tables. And then we have the full SQL at our disposal to do all this analysis. And this is basically what's embodied in SIMSQL, which is a really cool system that does this. Okay, so since I'm running short on time, I think I'm going to sort of stop here and quickly jump to the summary for my part, which is that you can get a lot of mileage for machine learning just by using SQL and UDF. And a lot of this work has very deep roots in database management system extensibility research. And it also has roots in array DBMS and specialized system people have developed over the years that handles matrix-like data. So next up, Arun is going to talk about even more opportunities for doing joint optimization when you have deeper ML plus DB integration. All right, and I'm going to switch you to the...
Should I read this?
Yes. All right. Just 1 second, sorry.
This one. Yep. Okay, great. Thank you, Jun. And let's all give Jun a round of applause for the immense amount of work he has done. Firefighting all the way till this morning. So thank you, John. It's really remarkable watching you do all that. And thank you for your service. So, and thanks everyone for coming. I know it's a Friday morning, but I appreciate all the enthusiasm. So let's get started with deeper integration of data management. Oh, I think this is blocking, but that's okay. Deeper integration of data management and machine learning. And I'll start with learning over joins, which is this recent research topic that has emerged to address this particular problem. Many data sets in the real world are multi-table with features spread across multiple tables connected by database dependencies, such as key foreign key dependencies. But most ML toolkits, including all the in-database toolkits and memory toolkits, expect the training input to be a single table where all the features are available together. And this forces data scientists to join all these tables and materialize the output table that concatenates feature vectors from all these input tables. So in this example, here you can see like maybe you have 3 tables in a star schema, and then you materialize the output of the joins. And as database folks, we know that materializing output of joins could lead to a lot of overheads depending on the data input sizes. It could lead to extra storage overhead. This intermediate table could be massive, in some cases over order of magnitude. It could lead to computational redundancy. Because the joins introduce redundancy, machine learning computations over that intermediate join output could have a lot of redundancy in its computations, which wastes a lot of runtime. And the join time itself, as we know, could also be non-trivial. And finally, input data in the real world is rarely static. It keeps changing, new tuples get added, and asking the data scientist to maintain this intermediate file somewhere introduces extra headaches for them. And so the learning over joins is basically a paradigm that recognizes that in the database world, we have this very celebrated query optimization idea of pushing the select through joins. We have extended to pushing projections and aggregates through joins. And so in this body of work, essentially we want to push machine learning computations down through joins to the base tables so that you do not have to construct this materialized output of the join. And there are different approaches that different systems have taken, and I've grouped them into 3 categories. The first one is you want these operations to take place over existing standard data processing systems, such as relational data systems, Hive, Hadoop, and so on, and a bunch of tools that I myself have worked on operate in that space. I will talk briefly about them, Orion, Santoku, and Morpheus. And more recently, people have also integrated machine learning over the so-called factorized database and factorized join representation. This is Dan Otonu's work. I see Dan is here in our audience. And FDBF is a tool for linear regression algorithms that basically push these computations down through joins over arbitrary join expressions. And finally, there's also a body of work that focuses on specialized algorithms and specialized data representations. LibFAM is a tool for factorization machines, which is an increasingly popular algorithm. And they encode that over a so-called block structured data set, which is a form of compressed representation. There's TensorDB, work from Selçuk's group, which essentially pushed tensor decompositions through joins, and compressed machine learning, where you compress the data in a lossless way and apply machine learning on top of those compressed representations. Now, this body of work that is related to learning over joins, but it's actually orthogonal, and that's the field of statistical machine learning, statistical relational learning, where you want to basically learn over databases that have very general database dependencies. Deep dive system from Chris Ray's group is probably the best example from our community of a system that scales statistical relational learning to large amounts of data and applies lots of new techniques. But there are a bunch of other work from our community, from Lisa's group and Rasha's group and so on, that have applied database style ideas to statistical relational learning. Okay, let's dive into learning over joins over standard data systems. Let's start with the same example that Jun introduced very nicely, gradient descent. And here we're focusing on generalized linear models. Think logistic regression, linear SVM, and so on. And their objective function or loss function is essentially a sum over n terms, where n is the number of training examples of a function f that looks at the inner products W transpose xi, where xi is your feature vector, and yi is your class label or the target for regression. And the gradient expression is also a sum over n terms, and it's linearly separable, and it's an expression with the scalar function g. Again, you have the same inner products inside that function, and then you scale the feature vector xi. Now, in the learning over join setting, this feature vector can be partitioned into feature vectors over 2 tables that are the input to the join, xs and xr. And so the fundamental observation here in learning over joins is often these computations are separable over these features from the input-based tables. So in this particular case, for gradient descent, the inner products that you compute are linearly separable over the features from S and R because of the partial inner products being linearly additive. And so that's the main idea of the factorized learning work introduced in the Orion system. And because many of these gradient descent-based machine learning algorithms are easily implementable using existing user-defined aggregate implementation, as Jun explained, with this simple observation, it turns out that they can still be easily implemented as user-defined aggregates over existing data systems, and you can still get the benefit of pushing ML down through joins. And this has been shown on top of relational database engines like Postgres, and also on top of Hive and Hadoop, and on top of Spark. In the Morpheus system, the authors generalized this idea of factorized learning. Initially, you had to understand the access patterns of these individual algorithms and manually rewrite the implementation to get a new piece of code that runs in a factorized fashion. And in the Morpheus project, the idea was to mitigate that development overhead. If we can get a formal representation language for large class of ML algorithms, and if we basically push those operators of that language down through joins, then we can automatically factorize any ML algorithm representable in that language. And in the Morpheus work, they recognize that linear algebra, as Matthias will be talking about, is a language to represent a lot of ML algorithms using matrix computations. June showed ordinary least squares, how it's basically an expression over operations over matrices, k-means clustering, non-negative matrix factorization, several other algorithms can be represented as programs in linear algebra. And so by factorizing these individual operators, matrix vector multiplication, Gramian matrix, scalar matrix multiplication, and so on, the Morpheus framework essentially pushes down these linear algebra operations through joins, thus automating, taking a first step towards automating this idea of learning over joins. In the Santoku system, the authors extended this idea to not just computations that take place over numeric feature spaces, but also discrete feature spaces. It's a toolkit in R where they extended this to algorithms like naive Bayes, decision trees that involve feature ranking and feature selection. Now coming to the factorized database system, the factorized database is essentially a new kind of database system that exploits the distributivity law of relational cross-product over unions to come up with very succinct representation for databases and applies relational operations in a factorized fashion to improve runtime performance, to reduce storage space, and so on. And in the FTBF work, the authors essentially observed that for linear regression, they introduced a new algorithm that computes the Gramian and then applies gradient descent on top of that, which essentially avoids the need to access the data for every iteration. You compute this Gramian, the cross-product matrix statistic once in a factorized fashion, and then you use that statistic for multiple iteration. And in the factorized database work, they introduced this notion of an F-tree that helps you specify what the join order should be for a general normalized database. And so this generalizes to different kinds of joins in a more generic fashion. And more recently, the authors also introduced a semi-ring-based formalism for unifying aggregate computations that involve SQL-style aggregates like sums and averages and the linear regression aggregates that I mentioned to factorize these aggregates in a more generic fashion. Now, in the interest of time, I will just be brief about the work on statistical relational learning, but at a high level, you can think of statistical relational learning as a subfield of machine learning that focuses on combining earlier work on logic-based AI, where you specify first-order logic rules and constraints, with statistical AI, where you introduce uncertainty and learning of weights. And in a database sense, you can think of these as machine learning models that operate over non-IID data. So in traditional machine learning, your training set is assumed to be independently and identically sampled from the underlying data distribution. Here, you do not have that assumption of IID across the training examples. And in the database sense, that means you could have complex dependencies across the features of those examples. It could be multi-value dependencies, embedded multi-value dependencies, joint dependencies, and so on. And for more details, Lisa Gatour, who straddles both communities, has a nice tutorial at NIPS. She also has a textbook on SRL that I encourage you to read. The key observation from the database community is inference and learning with SRL techniques often requires joins internally. And so many of these ML algorithms for SRL actually perform joins. And in recent work from Chris Ray's group, they observed that if you can express these algorithms on top of an RDBMS, you can exploit the sophisticated join implementations that RDBMSs already have, rather than doing naive nested loop style joins that existing in-memory tools for SRL did. And that's the Tuffy system. Subsequently, they generalized it and enabled scalable factographs with Gibbs sampling. Jun mentioned that in brief as well. And also extended to incremental computation with incremental deep dive. And finally, just to wrap up this portion of the tutorial, there's increasing interest in actually pushing ML, taking that and running all the way to modifying the DBMS kernel itself. And SAP had a recent paper in SSDBM where they talked about creating new linear algebra kernels inside the RDBMS. And they came up with new compressed parse row and column representation for representing matrices. And they integrated an API for different access patterns for computations on top of these matrices and linear algebra operations. I mentioned how many ML algorithms can be expressed as linear algebra operations that can be optimized by the RDBMS kernel itself rather than as on top as UDFs or query generators. And finally, they also looked at, sorry for that thing being blocked, OpenMP-based shared memory parallelism for modifying the task scheduler itself of the DBMS kernel to exploit the access patterns and the parallelism available in these machine learning workloads. Now, of course, this is just the first step. I know from Oracle that they are also looking at making changes to the DBMS kernel and exposing R as a first-class language to access the data, bypassing SQL as well. So these are still early stages. Great. With that, I will pass the baton back to Matthias.
So are there any questions? That's the perfect time to ask them.
Yep. Oops.
Okay, is that good? Bring up number 4, and if you need to enable audio. Okay, so then just 4. Okay, excellent. Excellent, where is the pointer? Okay, thanks. All right, so now we've heard a variety of different integration approaches into DBMS. Now we shift gears a little bit and look at how do we actually build machine learning systems from the ground up and still exploit traditional data management techniques. So it is interesting to notice that a lot of those optimizing compilers for machine learning programs share a lot of commonalities with traditional query optimization. For example, you see similarities in terms of rule-based and cost-based rewrites and operator selection, but also in terms of providing different physical operators and operator selection. However, the operations are, of course, very different. So we deal with linear algebra operations over DAGs, not just trees. We deal with conditional control flow and very specific sparse and dense matrix or page layouts. Now, in terms of optimization scope, let's look at a simple example. So here we see an example of a conjugate gradient method for linear regression. What we see, we read 2 matrices and we compute an initial gradient and then iterate essentially iterations where we compute conjugate gradients until we reach a target norm. Now, there are different systems that follow a different optimization scope. So, for example, the Morpheus system interprets individual operations where the optimization scope is limited to this one single particular operation. Other systems rely on lazy expression evaluation. So we have Sebastian here for Mahout Samsara, for example, where you lazily essentially collect a DAG of operations, and triggering actions such as a write or a sum then essentially forces to optimize and execute this entire sub-DAG. Yet other systems, such as SystemML, essentially try to take the entire program and compile it down to efficient runtime plans with the scope of the entire program and the entire knowledge of all operations across the entire program. Now, during this optimization, we essentially apply a variety of different optimization techniques. A variety of systems include traditional programming language rewrites. This includes common sub-expression elimination, constant folding, and once we folded those constants, we can often even remove entire conditional branches. However, many systems also implement algebraic simplification rewrites specific for linear algebra. So for example, this trace over a squared matrix multiply, so the trace takes the sum of all the elements on the diagonal, can essentially be simplified to an element-wise multiply of our two matrices and a full sum over that. So notice that this particular rewrite changes essentially the complexity from cubic to squared, and with that leads to large improvements on large data. Some systems also support so-called loop vectorization. So the core approach is essentially to take the loop range and substitute our indices essentially with that range in order to completely eliminate this loop structure, which is important because a lot of systems rely on copy on update for those individual matrices. And it significantly reduces, those kinds of simplifications significantly reduce the number of intermediates and potential evictions from the buffer pool. Finally, we also have a couple of papers that try to perform incremental computations. So for example, the LinView approach tries to compute delta update rules. So remember, June presented kind of a closed form linear regression where the core bottlenecks are really computing the matrix multiply of tx and x and tx and y. The intermediates are very small, feature by feature and feature by one. Now, you can just simply take those intermediates and for any delta x and delta y that comes in our system, simply perform just an additional matrix multiply over the deltas only and add it to your intermediates, and with that gain efficient incremental maintenance. Another very important simplification rewrite is the so-called matrix multiplication chain optimization. Here the problem is we have a chain of matrix multiplies and we want to find the optimal parenthesis for this entire chain. Now, let's consider our example of txx and y again. Now, by setting the parentheses in that direction, there's a question. So tx is the transposition of our feature matrix x. T is really just the R notion for transpose. Okay. Now, by setting the parentheses in a correct way, we see for this very small example, we reduce the number of floating point operations by more than three orders of magnitude. Now, naively enumerating all those different combinations for an entire chain, of course, has an exponential number of different plans. However, the traditional conditions for applying dynamic programming apply here. So we have an optimal substructure and we have overlapping subproblems where we would redundantly essentially evaluate the same subchains over and over again. Hence, we can apply a textbook dynamic programming algorithm that is used in different systems. So we use it in System L. Riot extended it for essentially including I/O costs, and SAP HANA proposed a system that tries to incorporate sparsity estimate by maintaining fine-grained sparsity and computing essentially aggregates for sparsity of the intermediates as well. The best known algorithm, however, is n-log n, typically not implemented because it's rather complex, but and not really necessary because usually we don't see chains of matrix multiplies that exceed tens of matrix multiplies. Now, just to give you a rough example how it works, so here we have an example chain of 5 matrix multiplies. Now, this dynamic programming algorithm essentially uses an n by n cost matrix. So initially, okay, multiplying individual matrices have no costs at all. Subsequently, we evaluate the costs of multiplying all pairs of matrices. And now at the third layer, it gets interesting. Now we essentially consider different plan alternatives. So we consider, should we first multiply M1 and M2 and subsequently M3, or first M2 and M3 and subsequently M1 from the left side. Yeah? And we continue to fill up the entire cost matrix. While we fill up this cost matrix, we also maintain the path we've taken to arrive at those costs, which gives us a so-called split matrix. And then it boils down to essentially recursively reading out the path in that split matrix to arrive at the optimal parenthesis for our matrix multiplication chain. Now, the open resource questions here are how to extend those kinds of dynamic programming algorithms essentially for DAGs of arbitrary matrix multiplies, including other rewrites such as common sub-expression elimination and other operations such as element-wise operation, transpositions, and similar things that currently split entire chains of operations into subchains that are optimized individually. Now, one level down, we essentially look at physical rewrite. So a common rewrite is, of course, distributed caching, where we, for large-scale machine learning, try to spend executor memory to cache large matrices in aggregate memory. And there are different approaches. For example, Emma takes a very aggressive approach and caches every intermediate that is consumed by at least two subsequent operations, where we in SysML use a very conservative approach of just caching initial reads and any read-only variables in front of loop structures. A lot of data parallel frameworks also support partitioning exploitation. So consider that one input matrix is already hash partitioned. This allows you essentially to perform a very efficient distributed join by just hash partitioning the other input and then just over known partition IDs join instead of join over all combinations of partitions. Other data flow optimizations are, for example, an exists unnesting. So, for example, Emma transforms filters with certain broadcasts that are our probe set. They transform that into joins in order to expose it to the optimizer and include into a traditional join enumeration. And finally, a very high impact have, of course, the selection of physical operators. Let's look a little more in detail into those physical operators. Usually they try to exploit data and cluster characteristics. They try to incorporate data flow properties as well as the individual specific patterns of certain operations. Typically, we see a certain selection preference there. So whenever your matrix multiplies fit into local memory, then you usually apply really local linear algebra at your driver in order to avoid this distribution overhead latency and just partial aggregates. If those do not apply, we fall back to for certain patterns to special purpose operators. So there are special patterns, for example, for the transposition of x multiplied with x, which is known to be symmetric. So you know you only have to compute the upper triangle. And because you never want to materialize the transposition of x, you essentially can cast it into a unary operator that really just in a data local manner streams in those individual blocks. The next preference step are usually broadcast-based operators, where one input is very small and we just broadcast it to all the executors and again stream our large input matrix into those physical operators. If those operators do not apply, then we fall back to either partitioning exploiting join-based operators, or the real worst case are really repartition, similar to repartition joins, full shuffle-based operators where we have to shuffle our matrices, bring them together. Now let's use an example. So here again we see the core of a direct solve linear regression where we, in a closed form, compute essentially our model. This is supported by Mahout Samsara, by SysML, in terms of physical operators for transpose self as well as broadcast-based matrix multiplies. So how does it look like? Our distributed matrix usually looks like this. It's blocked in a certain format. In SysML, we use fixed size logical blocking. Now, an initial step is on the first operation over x, we essentially bring it into aggregate memory. So we persist it into a certain storage level. Subsequently, we compile a physical operator for this transpose self, which essentially does partial aggregations, and there's a final fold for the final aggregate of the final sum of those small matrices. Now, the same cached intermediate is now also consumed for the broadcast-based operator, where we have the transpose of y. So y is really just a vector in the number of rows. If it fits into the remote memory budget, we broadcast this to all the executors and do a similar unary operation. You might notice that there is no transpose of x. So here we also see kind of a physical rewrite where we flip the entire computation. So we can essentially exchange the left and right input of a matrix multiply by doing the transpose over left and right input and the transpose over the output, which allows us to avoid transposing the large feature matrix. Now, there are certain circumstances where just looking over the patterns would force us to do multiple passes over our matrix or materialize dense intermediates. Now, the goal of those fused operators is to essentially reduce either the number of scans or the number of intermediates. One example for that is the so-called matrix vector multiplication chain. This was the core of the inner loop of the conjugate gradient that I've shown you before. Now, you notice that we have essentially two matrix vector multiplies, and the data dependency in between forces a second pass over X. The key insight here is that this intermediate, however, is created and consumed in a row-aligned manner, which allows us to compile a fused operator that scans each row once, computes a scalar intermediate, and immediately scans this row again in order to compute the final output. And for the common case of tall and skinny matrices, individual rows fit in your L1 cache such that it looks like you're reading it just from in memory just once. Other fused operators that are commonly applied are, for example, the sum over the product of certain matrices or vectors. Here, creating those intermediates, so writing into main memory and reading those intermediates again, is much more expensive than the actual multiply operation or sum operation that we have. So a lot of systems try to essentially provide fused operators that just read all the inputs and compute all the entire chain of operation in one shot and produce the final aggregate. And of course, there are a lot of machine learning specific operators that have potential for that fusion, including sample proportion or SIGMOD. Now, so far we discussed kind of preventing intermediates and avoiding the number of scans. One large class or one opportunity for fused operators is sparsity exploitation. So, for example, here we see a very common loss function, which is weighted squared loss, where we try to evaluate a low-rank factorization, how close to our sparse ratings matrix is it already? In order to do that, we have to perform an outer product-like operation that creates a huge dense intermediate in the dimensions of our sparse input matrix, but dense. Yeah? However, the key insight here is that sparse drivers, so a sparse matrix with a sparsity-preserving operation like multiply, where a zero on the left-hand side would prune away any computed intermediates, allows us to compile one fused operator that selectively iterates over non-zeros and just selectively computes dot products for the final output. Other approaches taken in Cumulon, for example, take another approach, a more generic approach of taking a sparse matrix. So here O divide is again kind of the sparse driver. So we have a sparse matrix, sparsity exploiting operation. And what we do is essentially to compute a mask, which is a Boolean matrix where non-zeros exist in our matrix, and feed this sideways into all the operations on the other side. And those operations then only compute intermediates that are really required for this particular mask. Now, the open questions are really how to do that automatically and how to handle special values such as NaN, similar like for sparse linear algebra. With NaN, sparse linear algebra is actually invalid because 0 times NaN gives us a NaN and not a 0, so we would actually miss NaN output values. Usually this is ignored by many systems. The challenge is to how to kind of preserve performance but still support those special values. Now, how can we automatically generate those kinds of fused operators? So, of course, there's a large development effort associated with implementing all combinations for different sparse and dense inputs and for certain patterns of operations. So, we really want to do that automatically. And there are two main approaches what is typically applied. So one is just loop fusion, where we see, like on the right-hand side, an expression of matrix operations can be viewed as essentially multiple loops that create intermediates into main memory. And the goal of loop fusion is essentially to bring this all together into a single loop structure that creates just one output. Yeah? In SysML, we use a slightly different approach where we use a certain access pattern and templates, which allows us to implement cache-conscious data access and multi-threading in a skeleton of templates and just generate the very custom body for the inner loops of our fused operators. Additional techniques include, for example, tupleware, which applies very interesting micro-optimizations, such as deciding on generated code based on selectivities of certain predicates, similar to micro-optimizations in DBMS as proposed a couple of years ago, and tile-at-a-time computation, because you can imagine that compiling everything into one loop suddenly performs many more different instructions. So they try to find a sweet spot between essentially data locality and instruction locality. Now, the open questions are, especially for sparsity exploiting operators, how to optimize those kinds of fusion plans. And you can imagine if you have DAGs and a single node with multiple consumers, you have a choice between materializing an intermediate, which is expensive because you write in memory, or redundant compute because over those multiple consumers, you might arrive at the same operation multiple times. Now, all those optimizations work really great if you know sizes. And most systems assume, or academic papers essentially assume that those sizes exist. Unfortunately, this is not the case in practice. So there's a number of use cases, such as conditional control flow, complex function call patterns, where you're not aware, or if a certain function is called with multiple sizes, you're not allowed to propagate those sizes into this function to compile efficient plans. In those cases, we usually fall back to very conservative distributed runtime plans, essentially to the worst case for all those physical operators. Now, how this is typically approached is with either lazy expression evaluation, which greatly simplifies the compilation process, because suddenly you only deal with unconditional DAGs of operations, where you know the kind of sizes of intermediates, and you have a very small scope according to exact statistics on the input, or dynamic recompilation. So especially for systems like SysML that have an optimization scope of an entire program, you have essentially for certain intermediates unknowns. And what we do is to essentially split DAGs at boundaries where certain operations create unknown size estimates. We flag entire DAGs for dynamic recompilation, and just during runtime, based on the exact statistics of your intermediates, we then propagate them into a partial DAG, propagate them, recompute memory estimates, and recompute essentially instructions for a basic block just before we execute it. Now, the open questions are really principled approaches for estimating the size and sparsity of intermediates. Because again, all optimization that I discussed before, most of them depend on size information. So having a principled approach to especially estimate the sparsity of intermediates is a precondition for all those optimizations and also for valid plan generation. And more generally speaking, in general, there's a huge opportunity for adaptive query processing and storage for those kinds of linear algebra programs. With that, we are at the end of the first of those two parts for how we perform optimizations and the runtime part. So are there any questions related to that part? Otherwise, I would just switch the slides. Any questions, please?
Do you have any numbers about how much faster this makes the system?
Oh, it really depends on the individual. Good question. Okay, excellent, thanks. So I'm really just used to track points, so I need a little help here. So it really depends on the optimizations. In general, especially whenever you change asymptotic behavior, it's almost unlimited. For fused operators, let's go to very common operations, for example. It's a little... Yeah. It's just slow. Okay, let me... So for different physical operators, for example, or let's start with this example. Having operators that allow you to not shuffle your data, roughly in the ballpark of 4 to 10x, roughly. As soon as you compile fused operators, it is really, and those expressions appear in the inner loops. So usually for those operators, we see 2 to 3x performance difference. Not materializing those intermediates gives you easily a 10x, because it's really write memory bandwidth versus read memory bandwidth. And
this is faster on conjugate gradient descent?
Oh, so for example, this expression, the first expression, matrix vector chains, are the only operations that touch your large matrix in the inner loop of conjugate gradient. So getting a 3x there leads to end-to-end improvements on conjugate gradient.
But
yes.
Does it improve it such that it's faster than, say, limited memory BFGS or like Adagrad?
Oh, that is an excellent question. So what most of those systems for optimizing linear algebra, what they are doing is essentially they are at the level of you specify the algorithm. We want to support essentially that people can write their custom algorithms. So the optimization objective is just performance. So we do not aim to modify the algorithm automatically. So it really, so given a fixed algorithm with a fixed convergence behavior, this optimizes the runtime of those algorithms. We do not even try to select different algorithms. There are different systems, Arun will talk about them, at a higher abstraction level that try to optimize for accuracy and runtime, essentially selecting those different algorithms. It's really a stack of different systems, and right now, those systems are really, optimization objective is performance. Did that answer the question? Not really.
Yeah, so I mean, like, I guess what I'm kind of asking is that there's sort of like, I mean, there are other like to really say I'm going to focus on, you're focusing on conjugate gradient, but conjugate gradient isn't a very fast algorithm, right? I mean, like, if you have a larger data set, so if we started with a faster algorithm, like, are we actually, like, for the fastest algorithms, or can we actually make some of the fastest algorithms using these techniques in the future? Like, that's what I'm thinking about. Which, like, can we actually make the bottom line? I understand, and I totally believe that we could take an algorithm and make it faster, but, like, can we make the fastest algorithms using these techniques? That's my big question.
So what we've seen, so we use conjugate gradient because it offers essentially a very nice convergence behavior. So for example, it guarantees you that you converge, it guarantees you to converge in less than the number of features, which is usually much smaller than any gradient descent, right? So a lot of our algorithms actually use conjugate gradient because it has very nice convergence rates. So essentially, well, how is it? It's a meta-level question. It's hard to answer that. The algorithms we've seen, usually it is at many different dimensions very beneficial to have different optimizations, different physical operators, because they share very similar characteristics often.
Thank you.
Is it? And just while we are switching, I can't comment on LBFGS because we did not implement LBFGS yet. That's okay, excellent, thanks. All right, now we go one abstraction level down, and what we are looking at now is essentially, as I said before, a lot of those operations are iterative and memory bandwidth bound. Hence, it is crucial to fit your data into memory, which applies to single node setups, aggregate memory, and even accelerators like GPUs, where it's important to fit it into device memory. Now, often we have matrix vector operations in those kinds of convergence-based algorithms. Second, we usually want to reduce the number of reads and writes, and hence reduce the number of intermediates. Just to give you a flavor how common data characteristics usually look like, usually we have tall and skinny matrices where the number of rows is significantly larger than the number of columns. You see a non-uniform sparsity where sparsity varies among features. So here you see 3 sparse data sets with essentially the sparsity skew in the number of features. Furthermore, you often see low column cardinality in terms of number of distinct values and correlations between individual columns. Now, in order to really prove that we deal here with memory bandwidth bound operations, so this is just a single node with peak memory bandwidth and peak compute. Now here we look at a roofline analysis that essentially plots operational intensity, how many floating point operations do you execute per byte transferred from main memory, versus maximum attainable floating point operations. And the horizontal line is essentially peak compute, whereas those diagonal lines are essentially your maximum memory bandwidth. This gives you a roof line, and now you can map your applications and determine very easily what is the limiting factor in your application. So for example, for matrix vector and those matrix vector chains, they are really just memory bandwidth bound, and this is by almost 40x, and hence it is important to optimize kind of the reading of those individual matrices. Now, just to give you a background of how matrices are usually partitioned and their layouts. So usually we have blocked matrix representations where, which are also called tiles, chunks, or pages. And either people use logical blocking, where you have a logical fixed size, which leads to physical variable size, or physical blocking, where you try to have similar physical sizes, but this greatly makes the joint processing in distributed environments more complicated. Now, how do commonly those block representations look like? Let's take an example. The easiest one is certainly a dense representation, where we usually just use linearized arrays. The most common sparse representations are so-called compressed sparse rows, where we have 3 arrays of row pointers, which are offsets into index and value arrays. And then for CSR, you have column index arrays, and finally a value array for the individual values. There are extended CSR representations that essentially use individual sparse rows of column index value pairs, which allow you to very flexible append to individual rows. And the most flexible format is certainly coordinate format. As June discussed, this is just IJV, so row index, column index, and value pairs. Now, let me give you, and in the interest of time, I try to explain the major aspects on this slide with all the overviews, and then I'm handing over to Arun. So there are a variety of techniques to address data-intensive machine learning. So first, we already discussed distributed caching, where we have executors and try to cache, use a portion of our executor memory for caching. Subsequently, there are a variety of techniques for essentially compression to reduce the size of reused intermediate matrices and perform linear algebra operations directly over the compressed representations. There are approaches for scan sharing, where we essentially try to transform many scans of our matrix, which are memory bandwidth bound, into one compute bound scan over the entire matrix. There are index structures for out-of-core operations, as well as to improve data placement in NUMA architectures. And especially with regard to NUMA, there are also works that try to balance essentially hardware and statistical efficiency by deciding upon model and data replication. And finally, there's some work on buffer pool management. Again, in the interest of time, I'm going to skip over the individual details right now. We have a lot of pointers in the individual slides. We will post them online. And whenever you're interested in any of those individual categories of techniques, please just talk to me after that. And with that, I guess, since we're really running out of time, I'm handing over to Arun. Thank you.
Great. Thanks, John. Okay, thank you, Matthias, and thank you, John, for helping with this. Yeah, in the interest of time, I'll also be as brief as possible with the last portion so that we don't keep you from your coffee. Let's get started. Coming to the last part of the tutorial, I will talk about lifecycle issues that go beyond just individual training and inference computations and look at the end-to-end picture of building and deploying machine learning models. And for those of you who were at my keynote talk at the Dean workshop on Sunday, there will be some overlap, but it's worth reiterating these points. So what are these lifecycle issues? When you are building data-driven applications that use machine learning, often the data scientist is in the loop in order to build these ML models and then deploy them in production systems, cloud services, and so on. And you'll have to maintain these ML models over time as the data evolves. And they use a variety of tools, relational systems, SysML, Spark, Hive and Hadoop, in-memory tools, R, scikit-learn, SAS, TensorFlow, and so on. And so this life cycle takes place on top of any of those systems. And there are major issues that are yet to be addressed in depth and that require the attention of our community. And in the context of building ML models, a couple of major issues are data sourcing. How do you even figure out what the features you want to start with are for your machine learning task? The other one that I'll focus more on are feature engineering and model selection. And in the context of deploying ML models, there's the challenge of model serving, deploying these models into production systems and using it for inference at large scales. And the loop between inference and learning is tightening as the models get updated ever so frequently. It used to be once a quarter, once a month, once a week. Now people want to do it in real time. There's also the challenge of model management. You often learn a large variety and a large number of models through this life cycle. You want to be able to maintain and track them and learn from these models for future iterations of this build deploy cycle. Now, of course, this is not an exhaustive list, but this is a key set of problems that I think our community has a lot to contribute to. Let's dive into feature engineering. Now, what is feature engineering? Essentially, it is the process of obtaining a formal representation of a data generating process as structured feature vectors. For any machine learning model, they operate on a feature representation. Now, it goes by various names: feature learning, representation learning, and so on. Why is it that we as data management folks need to worry about feature engineering and not just the ML folks? Well, historically, ML folks have had the tendency to brush aside feature engineering under the carpet in their publications and their tools, and often high-quality features are the secret sauce for winning ML systems in practice. Like many data-driven applications, data scientists often spend up enormous amounts of time on just getting really good features. Many of these feature engineering operations that take place in practice are data transformations. And that's why our community, which is probably the best community to talk about data transformation, should be involved. What sort of operations take place during feature engineering? It depends on the data type. If your data is already structured and you have categorical and numerical variables, then you need to do whitening, you need to do feature selection, subset selection, ranking, joins, which we already talked about with learning over joins, where you have to integrate features from different sources, principal component analysis, and so on. If your features involve text, like reviews or comments, you often use text features like bag of words, parsing-based features, domain-specific, dictionary-based features, and increasingly with deep learning, embeddings, such as word2vec. If you have images, audio, video, even time series, the state of the art today is deep con nets and deep recurrent nets. So feature selection is one particular task that takes place during feature engineering of structured data, and I'm going to give a more detailed example about this particular operation and what our community can contribute here. In the context of the Columbus project, the authors observed that feature selection in practice is often not a single algorithm, but a human-in-the-loop dialogue process where the data scientist explores different algorithms. And this is primarily because they want to obtain more insights about the data generating process. Here's an example of, say, customer churn prediction, which is perhaps one of the most ubiquitous ML tasks in enterprise domains. They have a bunch of features about customers, their age, income, gender, and they want to do, say, churn prediction. The data scientist starts by evaluating the prediction error for their favorite classifier with all features. But then they want to understand how useful is it to obtain demographic features from customers. And the motivation could be maybe they want to lower the overhead of collecting information from customers when they sign on to their insurance policy. And later they want to add maybe certain demographic features are useful to have. And then they want to consider other features like for car insurance risk pricing, should we collect data about the cars, weather, and crime, and so on. And so it ends up being this human-in-the-loop, data-driven process where they explore different features. And in the Columbus project, this recognition led the authors to encode a lot of these exploratory analysis tasks as declarative operations in a domain-specific language on top of the R and Python environments. And these operations are fairly simple. They just explore different subsets. You can specify different subsets for your regression tasks. You could use forward, backward, and standard stepwise selection procedures. And by exposing all of these standard operations in a declarative language, DSL, Columbus was able to generate optimized lower-level code on top of, say, an R-based system, and it basically acted as a code-generating middleware. And here, they were able to apply database-style optimization ideas like batching of data accesses, Matthias mentioned scan sharing, materialization of projection views because feature selection, subset selection involves accessing only a subset of the features, and also techniques from the linear algebra and the ML world like QR decomposition. When you're learning multiple linear regression models over different subsets, QR decomposition is a materialization optimization that helps speed up the runtimes. Warm starting, core set sampling for controlling the accuracy and runtime trade-offs. So there are other classes of systems that are emerging that are aiming to tackle these bottlenecks that arise during the feature engineering process. And some of these systems take a data flow-oriented view of the feature engineering process and apply database-style optimization. The brainwash system represents feature engineering as workflows of UDFs and then comes up with, basically makes feature recommendations based on profiles of past workflows. Keystone ML is a recent system that focused on operator selection at the level of algorithms, as the question was asked, for solve operation, which is basically a common operation in machine learning. There is the zombie system from Mike Caffarella's group, which looked at reducing the amount of work for evaluating feature codes and sub-selecting certain portions of the data that will be most relevant for those feature codes. These feature codes essentially extract new features from, say, raw forms of data, and they apply multi-arm bandit techniques to reduce the amount of exploration, increase the amount of exploitation, and do the trade-off between explore and exploit. In the Hamlet work, the authors showed that you can actually apply statistical learning theory and exploit database dependencies, such as functional dependencies, to throw away a large subset of features a priori, especially in the context of data integration, where you're fusing data from multiple sources. And I talked about learning over joins. It turns out that in many cases, exploiting these functional dependencies and key foreign key dependencies can actually allow you to avoid certain tables altogether. So there still remains a lot more open questions on how do we systematize this process of feature engineering. A data flow-oriented view is possible, but we also want to be aware of the semantics of the ML computations that enable optimizations. Moving on, I'll talk briefly about the model selection process. Model selection is essentially a higher level, more general process of obtaining a prediction function for modeling a data generating process that subsumes feature engineering itself. And in the SIGMOD record paper, the authors explain how model selection can be viewed as operating over a triple of options: feature engineering, which fixes your feature representation; algorithm selection, which fixes your hypothesis space of the models, as well as the learning algorithm to obtain an estimator model; and the hyperparameter tuning associated with the hyperparameters. Now, why is model selection important for our community? Again, all of these operations are very data intensive. They access the data repeatedly, often subsets of the data, and they access this multiple times. There is potential for a lot of database-style optimization opportunities in the end-to-end model selection process. And also, changing any of these options often affects the optimal point for the other options, and so they are quite interdependent and need to be viewed together. So what does the model selection process look like? Essentially, again, you have the data scientist in the loop, inevitably, and the data scientist decides what features they want and what model or algorithm they want, and the hyperparameter combinations execute on a system, any of their favorite ML system, and get the accuracy, consume the results, post-process the results, and then modify the configuration. Say, reduce the feature set, or modify, use a different algorithm, or use a hyperparameter tuning procedure. And this iterative process keeps taking place. Now, typically, data scientists do not think at this low level of abstraction of enumerating model selection triples. They think at a higher level of abstraction of, say, auto-tuning hyperparameters, or just fixing one particular algorithm for a model, or exploring only a subset of models, and think of features in bulk. So Systems that aim to automate this whole process and cut the data scientists out of the loop are helpful in certain scenarios, but what would be even more helpful is bridging the entire automation spectrum all the way from fully manual enumeration of MSDs to fully automated enumeration, which basically a developer of the system hard codes a few combinations of MSDs to explore, using abstractions, database-inspired abstractions to bridge this gap and figure out logical combinations could be potentially helpful. And that's the idea in this vision paper, where they basically propose the idea of declarative interfaces, could be on top of any favorite ML system. And under the covers, you introduce a middleware that does code generation and executes multiple models in an optimized fashion. And since the system is now aware of the higher level semantics of the process, we can apply database provenance style ideas for the model selection process to help the data scientists understand what is going on with these models and debug these ML algorithms. This potentially reduces both the number of iterations and the time per iteration because of the specification and the optimization potential. Now, of course, several old abstractions and recent abstractions can be retrofitted into this framework. And you can think of auto-tuned hyperparameter functions, which are very popular in, say, systems like R, as essentially exploring different combinations of PT. Columbus, which I mentioned before, can be viewed as exploring different combinations of FE. The ML-based system from the AMP lab automates algorithm selection and hyperparameter tuning, and that can be viewed as exploring different combinations of AS and PT. And these are basically declarative interfaces, some in hindsight, whereas you have optimized implementation of ML techniques, as we talked about so far, on top of different data processing systems as the lower layers, and model selection triples can act as sort of a narrow waist for bridging the higher layers and the lower layers to build more principal systems that provide more support for this process. This could also open up new abstraction possibilities that we have not yet thought of for combining these MSDs in intuitive ways. So just briefly about some of the other kinds of work in this area. I mentioned ML-based. They help automate some of these tasks by specifying a predefined search space with a finite set of algorithms. The Hemingway system automates cluster sizing in addition to algorithm selection and tackles the convergence problem by looking at the algorithm's execution over iterations, learning some statistics, and incorporating them into the optimization. There is also meta-learning cross-validation that the system ML folks have actually looked at lower-level optimizations for faster runtimes of cross-validation, feature selection, and different sampling schemes. There are many open questions in this space. We are only beginning to understand the data management aspects of the model selection process, but I think it's high time for our community to be involved because the ML community has studied theoretical aspects of model selection, but at scale, we have to worry about the data systems aspect as well. We could look at exploiting redundancies within and across model selection triples. Often they differ very little across iterations. Incorporating accuracy or other sorts of approximations and doing them in a principled manner is a major open challenge. Using visualization techniques, we have a lot of work on visual analytics. Using that for debugging ML models and helping understand the model selection process better would be very helpful. Okay, so in the interest of time, I'll skip the work on model management. Essentially, these class of systems treat models as data themselves in some sense and help with querying, debugging, storing, and retrieving models. And again, there are a bunch of open questions here. There are other life cycle issues, model serving, increasing the throughput or reducing the latency of inference for applications where a lot of examples arrive at high velocity. Sourcing the training data, sourcing the features, sourcing the class labels or the target, cleaning the data, pricing for data that is being purchased for ML tasks. There's a bunch of recent work in this space. And finally, building human-in-the-loop interfaces, visual interfaces, chatbot-style interfaces to basically make it easier for data scientists to do model selection would be very beneficial as well. Okay. With that, I'll stop now, and all three of us will be happy to take any questions. Of course, all these slides are available on the tutorial page, so feel free to go back and read it in detail, and also shoot us emails if you have any questions. But with that, I'll stop. Thank you.
Any questions? That's the time. So if there are no questions, just to recap, the two core conclusions are really, there is existing work to build upon. There's a huge landscape of existing systems with different abstraction levels. And it's very useful to be aware of those individual techniques. And we hope that we could give you kind of a survey of what exists out there. And our conclusion is really that the data management community can help in many different ways to really optimize and simplify end-to-end machine learning pipelines. And this really includes the integration into existing data systems, detailed optimizer and runtime techniques, and at the end of the day, just simplifying the entire end-to-end lifecycle. So bottom line is really, there's plenty of work to be done here, and we would really like to grow the community, especially with more people from the data management community. So, please.
Yeah, that's more of a practical question.
Absolutely.
So more recently that the deep learning field has really gained a lot of momentum on the industrial side, right? So notice that the company called NVIDIA stock price raised about 20% in the past 2 weeks or so. Mm-hmm. We're also happy to see that data management community is doing so much and on that direction. But my question is that, have any of this work done by our community being appreciated and recognized by the people who are generating revenue doing doing machine learning?
So I think yes. However, at the moment there is, of course, there are huge success stories for deep learning, and deep learning also has data management challenges, but it's a topic for its own. There's a good survey by Jack, I guess, and I guess the following tutorial covers kind of end-to-end pipelines and will cover specifically deep learning too. If we look really at data-driven products, I think a lot of those data-driven products include a portion of machine learning. However, there's also a large portion of just data pre-processing and just building the entire pipeline. So it is a part of really a business story, yes. It is not the sole driver of it. Yes. Please. Or do you want to add anything?
No, I think that basically covers what I had to say too as well. I think again with the model selection lifecycle, there is a lot of open challenges with deep learning as well, and a lot of these principles and techniques will matter for deep learning. The adage is that feature engineering is dead because deep learning is not there, but it's not really dead because there's model engineering and architecture engineering. And people are again now looking at automating that, but there's in the enterprise domains for structured data, the data scientist is still in the loop. And so we still have to manage the entire process. And as the models that are getting generated, as the model hub system showed, that becomes a data management challenge as well. And so there's still a lot of challenges, even with deep neural networks. You can think of them as different kinds of algorithms and feature engineering operations being fused together. Okay.
All right, then next question.
I think that's related a bit. It was a very interesting tutorial. This last part for me, it was most important one, like from my side, because from the selecting features, this kind of stuff, it could help a lot. And I work in a project with a company actually that use machine learning. And one thing that I think that the challenge is how to make them be aware, to know about it, what we're doing here. I mean, my question is, what do you think about, because here we're in a conference about database, basically, mainly. We talk about machine learning, and it's important. But on the other side, we have machine learning conference. So how to make these people be aware what we are doing here and make them use that? Because mainly we go for machine learning conference, then you see another part of this, not the part, what's supporting actually, or it could help a lot. What do you think that could help us to work together and make what we're doing here help there as well?
So I think the most important part is really reaching out to your potential customers. So for example, last week I was at ODSC East in Boston with like 3,500 data scientists who have a lot of challenges in terms of not just calling existing library functions for algorithms, but customizing the algorithms, making their regression robust, different loss functions, and there are a lot of customization, and it's really just reaching out and trying to bridge the gap, and just making people aware of what we are doing. And for us, the best way to do that was really to make our system open source. I think the same applies probably to TensorFlow too, that it really creating a community around it and just being open and trying to bridge the gap and not sitting in our silo and kind of doing our stuff.
Yeah, I agree. I mean, open source is a major thing. So we have to open source as much as we can, write blog posts about it, advertise it. And from academic perspective, I also want to attend industrial conferences where data scientists and practitioners gather. So that's something that I plan to do, and a bunch of others in our community are also doing. And also collaborate with ML people. So I collaborate with Jerry Zhu, Steve Wright, Kamalika, a bunch of ML people who actually publish in that community, and they are aware of this work, and they could spread the word. We could also go and present tutorials, and there's also workshops in the ML community. There's the ML systems workshop, and our community can increase our participation in such workshops to bring these two communities closer together.
So hi, so coming from the ML community, all for collaboration, and I think there's a lot of good stuff there. I think one thing that I would, this may be less of a question maybe, but I would encourage is, you mentioned multiple times that you were thinking about small numbers of features, and you mentioned a couple of times about conjugate gradient and guarantees. Well, conjugate gradient doesn't have guarantees if you're not actually in, like, you know, certain subset of problems that aren't necessarily the most interesting ones. And small numbers of features, there's a lot of problems, especially when you have lots and lots of data. You often don't have a small number of features. Even if you have a deep network, you might have millions or hundreds of millions of features. So I guess it's kind of, I would kind of encourage you to think about like large numbers of features. And I guess to make this a question, how do you think your community can help in the scenario where there's tons of features?
That is an excellent point. It was a simplifying statement to focus, and those scenarios exist. They usually originate from data warehouses, but you're absolutely correct. There are tons of other scenarios with huge numbers of features. And I think how we can really contribute to those kinds of things is adaptivity. Essentially, it falls back to automatically optimizing physical runtime plans. So whenever you have a scenario with small numbers of features, you want to compile completely different plans than for large numbers of parameters, where you suddenly, any operations over vectors in the number of features have to become distributed operation. And that's exactly what those kinds of automatic optimization frameworks aim for. Oversimplified it in terms of application, but I totally agree. You're absolutely right.
Thank you.
No. Yeah, I mean, I agree. I think we are, I mean, as a community, we are not tied to the ML or the optimization tribal wars. So any algorithm goes, and as far as my own work, I've worked with stochastic gradient descent, which is probably the de facto standard for large-scale learning now in the Bismarck project, and mini-batch stochastic gradient. Even for the Orion stuff, we looked at fully batch, conjugate, LBFGS, block coordinate and coordinate descent, mini-batch and stochastic gradient descent, Newton's method, all sorts of, the entire roster of optimization algorithms. And often the principles of the systems that we build are agnostic to some of these algorithms. Some of the specific design trade-offs and the cost models we build might depend on the data sparsity and the sparsity of the features. But I think for the larger end-to-end picture, I think irrespective of the algorithms, there are still a lot of techniques and problems that we need to tackle. And even within machine learning, irrespective of the ML algorithm itself, there are a lot of problems to tackle. And I think our community still has a lot more to contribute.
Yeah, so thank you guys for a very nice and informative tutorial. I'm actually agreeing with the kind of things you do here, because I'm also trying to do things along these lines. So, however, there is a growing voice in the community on this sort of separation between, you know, this sort of work that goes inward, right? You look at machine learning and try to understand how you could optimize it better using database technology, and by integrating closer to the database engine. And another kind of direction, which seems to be more prominent, at least, coming more from the systems people, where they see machine learning as a black box, and their let's say goal is only to, I don't know, serve pages to this black box, whatever, distribute and so on. And there is this growing voice saying that, well, in fact, you do not need all this, struggle, which is maybe more brainier, but after all, is a lot of struggle. You can just, have to think more about how you better distribute the data, how you, have a horizontal scalability of your system. And so what are your thoughts on this?
I think it's not exclusive or. Their kinds of systems contributions also matter. It entirely depends on the application and the user and the workload. I think a lot of the end-to-end process depends on the semantics of what exactly you're computing, and that could help you optimize that better. And taking a black box approach will inevitably lower some of the optimizations that you can do. And a system that is not aware of what is going on can only help so much with, say, provenance management. So with provenance, you'll have to look really at the semantics of the computations. And I think there's an entire spectrum of opportunities. And the systems folks will do what the systems folks know. The data folks have to do what the data folks know. I think we don't have to compete with the systems folk. I think their work is complementary to the kinds of stuff that we can do. And I think we can really bring to bear our expertise with a lot of the things that we have worked on with relational systems and relational algebra in this context. And I think speaking to the systems folks will also be helpful because they often have insights about operating things at very large scales that our community probably hasn't studied, like in the cloud computing era, in real-time and Internet of Things era. And that's also something that we are beginning to do as a community. I think that's really promising to do.
But bottom line, although it's not an exclusive war, you actually compete with these guys, right? If a company has to choose a product, which product will they choose is the question, and why should they choose a product, following your technology versus some other?
So here's the thing. The company that they're going to choose could be Google, Amazon, Microsoft, because they offer cloud services. They are actually integrating some of these techniques as well. So Google is actually thinking about some of these techniques on top of their data infrastructure. So like I mentioned earlier, what is a data management system is changing, and some of the principles that we are developing will be applicable even at these large scales. Google, Amazon, Microsoft cloud services might be replacing Oracle, DB2, and so on, but a lot of these techniques and ideas will be applicable regardless of the system environment that you're applying to.
Yeah, so there was one part of the tutorial which we had to cut out because of time, which talks about resource elasticity. If you do large-scale machine learning, nowadays it's a lot of times you run in a large cluster or public or private clouds. And there, we try to stress the point that you have different layers or levels of abstraction, right? So you can really approach it from the system level where things are really black boxes. And you can move up one level where you talk about these operators, which we know semantics about and so on. And then even a level on top of that where you know exactly what are the machine learning algorithms that you can do. And you will see interesting techniques for different things like provisioning and handling failures that can be applied at these different abstraction levels. So in a sense, I agree with you, sort of different systems, they compete, but at the same time, the optimization techniques that you can identify at these different levels, they complement each other. Right? So you could have a system underneath which you use for, say, for example, execution or storage, and then maybe on top of that, another middleware system that's aware of this higher level of abstraction, which provides additional optimization.
So I think that was an excellent question, and I thought a lot about that. So I think for those different abstraction levels, there are good use cases. So sometimes just using an existing large-scale machine learning library, that is great. That gives you a textbook algorithm for large scale. Or using just R over partitions of data, sometimes it just gets the job done, absolutely. However, in a certain sense, those kinds of hard implemented libraries and black boxes essentially are constraints. Constraints for yourself, what you can do in terms of modifying your algorithm. And what I've seen in the past is that as we essentially create more and more of those data-driven applications and see more diversity, that at one point your algorithm becomes actually your competitive advantage as soon as many companies around you use exactly the same black boxes, you're suddenly willing to actually spend effort on building your custom, robust implementation that's potentially domain-specific, tailored with certain loss functions to your particular problem. So what I've seen over the last couple of years is really that at least there's an increase in custom analytics where people want to compose arbitrary algorithms and not just use black boxes. But there's a use case for it too. So hence I agree with Arun what he said, that it's really an or. But I see kind of a trend that more and more custom things are built too.
And let me just add one philosophical point. Often when communities that have expertise in certain topics like declarativity, optimization, provenance do not step in, it will be reinvented by some other community. And so you might end up seeing the systems community reinventing the principles and philosophies that we are doing, maybe in a crappier way, maybe in a better way, I don't know. And that actually could be a problem for the actual data scientists in practice, because they are looking to us to basically bring to bear our expertise with relational systems. With democratizing relational systems, we understand analytics, SQL analytics, data cubes. So this is just advanced analytics. So we could bring to bear our expertise to help these data scientists in practice, to help these software engineers who are building these systems in practice, rather than wait for some other community to rediscover and redo all this stuff.
So I guess there was one question by Benny, and then have we Joy, and then from Google. Oh, the captured the mic.
I have a microphone, so I'll go next. I would just like to add to Dan's point. I think there is some overlap and competition with the system folks. I think it's healthy for us to recognize that community is also working in this area. Competition is good. At the same time, I think as a community, we need to understand that there are more problems in this space if we look at the data side of things. And there, I think we have the advantage of having more know-how, of having more technical expertise than the system folks. And actually, they recognize that, and that's a good thing for us.
That's an excellent point.
As a disclaimer, I'm one of the presenters of the next tutorial, which will go into these issues. So that was a shameless plug on my part.
Take the mic away.
Thanks for the enlightening tutorial. So I had a quick question. This is a technical question. Can you actually learn the model selection process? Can you use prior model selection process? Can you use machine learning techniques to actually guide future model selection efforts?
That's actually a very good point. So for example, the ML-based Tupac optimizer at SOC 2015, I guess, what they've done is essentially they first model the search space of different algorithms, what your particular problem entails, different parameter combinations, and then they use a multi-armed bandit to essentially spend more time and more scans on those models that turn out to be effective. And so it's kind of a distribution. It's not just a grid search that looks at all of them, but a kind of a guided process. But Arun has the details.
Yeah, there is already work on that space. Google came out with an ICLR paper on using deep reinforcement learning to select model architectures for different conv nets and different neural nets. So there's already work in that space from the ML community itself. But they don't look at any of the systems-oriented aspects of it. And I think, again, it's one of those areas where we could actually collaborate and make those things even more practical.
Thanks.
Benny. You had a question too? Okay, that concludes our tutorial. Thanks for being here. And